And if people are interested, we also have a website which can go ahead and download. So I'm loading the data bit now from a cloud service. It's the Microsoft Cloud Service. It's the same part, but slightly different solution. And I could start this machining as well.
This is just looking at the process. It's not tied to the machine tool as the other one is.
Right, this one is a preview, essentially.
So this is dry running in simulation, or is it actually machine simulation?
It's not connected to a machine tool, so it's like
it's a machine simulation.
yes.
How do you? I'm sorry. Do you know? Can you retrieve the machine capabilities from that Okuma machine, so you know what its spindle capabilities and
Yes, the kinematics and all those. Yes.
are all available?
A lot of that can be modeled into AP242.
But not through MT Connect. You wouldn't typically transmit base machine capabilities through MT Connect. You would use 242 to do it. But if you wanted to know what the spindle horsepower, what the active spindle horsepower was or RPM was at the time, then you use MT Connect for that. Am I getting this right, guys?
The actual. So the actual.
The real-time data.
Real-time data.
Yeah.
The actual data comes through. It's coming through there. Yes.
So how would you know that, but the machine capabilities are captured someplace else, so you can't ask the machine for its capabilities, express capabilities, horsepower limits, axis limits?
That's done in the step model.
Okay, so that's the digital twin model, that's
Yes.
the static model.
Yes. But the real-time actual data, what it's actually achieving, is coming through the MT Connect.
Okay.
In fact, it comes through so often we have to be a little bit careful. You may see some flakiness about the update of the speeds here, because the speed is constantly going up or down slightly, and if we try to refresh that 100 times a second, all you're going to see is a blur. Okay. So we talked about the configuration of the machine down in Renton, how it's connected up to the digital twin. The digital twin allows us to see what's going on. If it's satisfactory, great. If we think, on the other hand, a change needs to be made, that's where our NC generation service comes in. This is a tool that came out of the DARPA ABM program developed by Penn State. I'd like to introduce, in a moment, Caleb Severin, who developed this. We are using it in two different ways. One is a general context where you give it two stage models. A stage model essentially is two models of the parts which are quite similar. Not just totally go ahead and make this shape, figure it out completely. Instead, we say, well, this is the as-is model, and this is the 2B model with a pocket in it. Go ahead and figure out the best way to go ahead and get me that pocket machined. By having two stage models, we make the whole process more tractable, because we're not relying on extremely clever feature recognition software. We're relying on the kind of feature recognition software that is available today. So we can use that to make machining solutions, or we can use it in a second mode where we already had a machining solution for our boxy part, only it was for aluminium, and using the Penn State software, we can automatically generate a complete solution, only in a different material. And they're very different materials. One's incredibly hard, and one is, in comparison, like putty. So, Severin, please.
Thank you, Martin. So, as Martin said, I will generate a new machining alternative for titanium, given a process plan for, it actually has two machining solutions, one for aluminum, one for steel. However, just as well, we might be addressing a usage case like real-time metrology indicating that something's wrong, So we need to change the machining plan, or machining a one-off part like an aircraft cabin where our approach trajectory has changed, and so we need different tooling or something like that. This is designed to run as a service, but for the purpose of the demo, I'll use a little interface here. The first thing I'll do is check a couple of check boxes. And this tells the tool to both extract the as-is and to-be stage models from an existing program and insert the machining solution we'll generate back into that AP238 program, as opposed to generating our own machining solution that would be in a different order possibly. And then I'll choose the AP238 file and just take this, open it up, see what we have to start. Once this opens up, we'll see we have a fairly detailed machining plan featuring 7 setups, 39 machining operations, and as I said, both steel and aluminum solutions. I'll point out that this AP238 data format is a hierarchical, high-level format, and that's what allows us to sort of flippantly talk about replacing machining operation. If this were a more traditional data representation, like a flat list of G-codes, it would be very hard to even demarcate a single machining operation, let alone a machining feature that might entail multiple machining operations. I'll quickly here navigate to setup 2. I'm going to replace a large pocket.
But we cannot see you because you're recording.
Oh, am I getting in the way of the projector?
Yeah.
Sorry about that. So I'll navigate to setup 2. This is the existing pocket. We'll actually be machining this later. I'll grab the name of the executable. So I'll need that quickly. Shortly. I'll also go ahead and tell the tool that I want to machine from the on the plus Y axis, because it'll save us a little bit of time searching the setup, not permuting the setups and looking for an optimal setup permutation. The last 2 sets of information I'll load are a parameter set. And this parameter set is largely what makes this a titanium solution. It specifies values for a lot of the decisions that we make. For example, whether we're going to use drill entry or helical entry, whether we will let the tool dwell or we need to wrap around corners, things like that. And finally, I'll load a tool library, and this tool library just happens to contain one of the tools we considered for the demo. It's a very good tool, so it's going to take the entire pocket in one depth of cut. While this is running, I'll sort of point out at a high level what it's doing. So right now, I just extracted the staging models. Then it'll calculate a removal volume, which is really just a Boolean. Then it'll calculate a visible volume, which in this case, because we're coming at it from a single setup, is the entire, oops, sorry, I don't have a master cam dongle in. That will happen during live demos. So this case being fairly simple, the removal volume decomposes into a single visible volume. The visible volume decomposes into a single prismatic volume. Prismatic volume having sides that are all parallel to the machining direction and equal height. We call that a candidate feature. We will run some analysis like manufacturability analysis to determine if we want to actually remove that in a given setup. Then we'll do sort of a depth first heuristic search. In this case, the visible volume decomposes into a single prismatic volume, and that will be a single machining feature, so it's kind of trivial. Now we launch MasterCam, because once we've identified a feature and looked at the tool settings and decided that in this case we want to generate 2 machining operations, because it so happens that the tool we provided has 2 settings. One is a high material removal rate, but can't handle small radiuses because we have to maintain a very constant chip load. And a second setting that can get into the tight corners, but it doesn't remove material as fast. And so we separate the machining into a bulk removal operation and a corner cleaning and finishing operation. I'm now opening the modified solution, navigating back to setup 2 in that pocket. And we'll see we now have a third option, suitable for titanium. We have a bulk removal operation and a corner cleanup and finishing operation. We are using MasterCam to generate the actual tool loops, tool paths, after we've we have an internal representation of an operation that's sort of agnostic to the CMM system. And then we more or less do a mapping from our operation to a Mastercam operation, copying parameters into semantically equivalent fields of a Mastercam operation. And then we kind of hit the easy button and say generate toolpaths for such an operation.
So you did a tool change between that pocket mill and the detail cleanup operation, right?
No, it's actually the same tool. In this case, if there had been only one tool that only did roughing and one tool that only did finishing, we would have done a tool change.
I misunderstood. I thought you said you had a couple different tools.
Oh, one tool, but it had different setting parameters for how that tool could be run.
Okay.
We provide settings that are appropriate for material entry, for constant speed roughing, and for finishing. If there are questions, I'll hand it back over to Martin.